All right, happy Monday, Tuesday. Somebody pointed out that they fixed the internet. They've gotten rid of the captive portal. Is this official? No?
Not yet.
Not yet. Okay.
They're working.
Awesome. Wow.
And right now you don't even have to sign in
Yeah.
to use the internet.
That's timely because I need to do an IoT project, and I've been wanting to do like a doorbell on my office that like sends me a text when someone rings it. And I can't do it because I can't keep a connection to the internet. So this would be cool.
Put your own router in your office.
Yeah, IT loves that.
And don't tell IT.
Yes.
And don't tell anyone I said that.
Yeah. Awesome. All right. Lots of stuff to go over today. So I want to talk about ODP 208. I want to announce that I will be here Wednesday and Friday morning at 8 o'clock.
Thursday? Thursday?
No. Tuesday, Thursday I'm at the gym. But tomorrow and Friday I will be in the digital lounge at 8 o'clock. I'm going to escape my office. If you want to go over PA1 or PA2 or both or ODPs or anything else, and you're not able to make my regular 9 o'clock office hours, right, you can find me at 8 in the digital lounge. That's this week only for now. We'll see what happens. So I got Wednesday, Friday hours. I want to go over PA1, make some general comments, but overall they looked excellent. Most people nailed it, or were very, very close. I'll show you some sample code. I want to talk about include files because there's still some confusion around those. I want to talk about make files because there's some confusion around those. And then we're going to go back to looking at PA2 type things in GDB. I want to take apart some structures using GDB, talk about different kinds of linked lists, doubly linked lists, circular linked lists, lists without sentinels, and then we're kind of done with lists for now. And we're going to go on to hash tables and hashes sometime today, tomorrow, Thursday, who knows when we'll get there. So any questions up front? I'm just going to embrace our new world order. Do this on the server. All right, so what is ODP 208? You're making a little linked list. So you are creating a function named build. It takes 3 integers and it returns a pointer to a struct node. And your struct node is the same as it was in previous ODPs. Integer data, struct node star next. All right, so what does it do? It takes those 3 integers, it creates 3 new struct nodes with the corresponding data values, x, y, z, the 3 arguments you were passed. And it creates a sentinel node. So your build function is going to call malloc 4 times to create 4 different nodes, each big enough to hold a struct node. Doesn't matter what the data value in the sentinel is, but the next value in the sentinel node should be the address of that second node you've created. Yes?
I have a question about the sentinel.
Yeah.
Because earlier on, it's easier for like the arrays because sentinel's the 0 node.
Mm-hmm.
But now that we're going into memory, it's starting to become kind of like nebulous in that like, are we supposed to know what the data in the sentinel node is? Are we supposed to treat it as the first node, or do we treat it as like this
Same as
other-
PA1, you don't care about the data in the sentinel node. The only purpose of the sentinel is to point to the first actual data node.
Okay.
And if there is no, if the list is empty, then the next field of the sentinel should be null.
Should we think of it as a node itself, or just as a pointer?
Yeah, think of it as a node itself, but it doesn't contain data that you care about.
So when we write insert, add, delete, search, ignore it.
Well, when you write search, for example, you would start from this node right here. So you would start from sentinel arrow next. When you do insert, you need to know the previous node as well as the current. So your previous will be the sentinel. Your current will be sentinel arrow next.
But in terms of data, we're not.
But in terms of data, you're only going to check the current, right? So you're never going to look at that data value.
Okay.
And then if you decide that you need to insert before this X, your previous is already pointing to the sentinel. So it'll just adjust that next field to point to the new node. Do you like my ASCII art? I worked hard on it. All right, so and yeah, in your main program, you're going to do something like struct node star. I don't know, you can call it LL. And when you call your init function, that creates a node somewhere, puts some magic value in the data field if you like, sets the next field to null, returns the address of that node, and this statement right here will set LL equal to the address of that node, which is the sentinel. So now anytime you use LL, it's pointing to the sentinel. And you pass that to your functions and they do what they need to do. All right, so build creates 4 nodes, right? One is the sentinel. The next field should be the address of the second node, whose data is X. The next field of the second should be the address of the third. Data is Y. Next of the third should be the address of the fourth. Data is Z. Next of the fourth should be null. And then you return the address of the sentinel. So this is where we got to be a little careful. Let's just make a list of 2 nodes. So you've got A and B. They're both struct node stars. They don't point anywhere in particular. Think of A equals 0, B equals 0. So if I say A arrow next, I'm going to get a seg fault. So we have to actually have A pointing to somewhere in memory that holds a struct node. So you do your malloc. And how much space do we need? Whatever the size of a struct node is. And do the same thing with B. So now you've got 2 struct nodes. If we want A's next field to point to B, it's as straightforward as this. The reason is that B is actually a pointer to this node. So B already has the address of the node. So when I say A arrow next equals B, I'm saying this is the address of that node B. And if I said something like return A, what I'm going to return is the address of this node, right? A is the location in memory where this node is stored. So when I say return A, I'm returning an address. So if this was in a function that returned a struct node star, and I said something like, you know, X equals function name, X will end up being the address of this first node. So sentinel node for 208, but whatever we decide to return. So getting this just right takes a few tries maybe, but try to believe that it makes sense when it works. And if you're in doubt, go into GDB or throw in some print statements. Right, print out the value of A, call your malloc, print out the value of A, do the same for B. Do this, right, and now take a look at what the pieces of A are, and you should see that this second field of A is some location in memory, and if you go to that location in memory, you'll find the data value of B followed by whatever you put in the next field. So once you can do this, right, PA2 is done. right? You've done everything that you need to do to be able to do PA2 if you rework PA1 to use these field dereferencers. All right, does that make sense? Get you going? All right. So, PA1. So it took me off and on 3 days to grade everything, because this is the biggest class I've ever had. For 222, we've got 65 people, which is awesome. But even if I can get through an assignment in 10 minutes, that's 11 hours. So it took me a little while. Plus the weather was nice, so it's working slower. But so PA1 looked really good overall. Okay, so it looked like the concept of a linked list and the basic algorithms for manipulating these linked lists, it looks like people have that down, which I'm really happy with, because that's the goal of PA1, is to get those concepts down. PA2, we go into this kind of dynamically allocated memory implementation. If you lost points in PA1, other than silly things, like not having spaces between the numbers and the output or something like that, if you lost significant points, number one reason was problems with the main program, to the point where I couldn't actually test the other functions. I could look at the code and see what you were trying to do, but I couldn't actually run it because the main program would either seg fault, or it would loop, or it wouldn't compile at all. And those are in some sense not as concerning to me, even though they cost you more points, because those are like CSE 224 kinds of issues. If you were having trouble with that, right, you definitely want to come and see me this week, because you're going to be having to write similar main programs for all of these assignments, and we want to get that figured out at this point before you go forward with PA2. So definitely come and talk to me, and a lot of times it's just nailing down this business of fgets, scanf, the return value from scanf, putting together an outer loop, things like that. As far as the linked list and issues with that, some cases where the delete function misbehaved. Sometimes delete would delete a bunch of stuff, or it wouldn't delete, or it would seg fault. And when I was able to track these down, mostly it was a pretty minor issue. For example, when you begin working with a list, you know that your sentinel node is 0, so you set previous equal to 0. But if you set current equal to 1, you're making an assumption that the first node was stored at index 1, and that's not always a valid assumption. So little things like that. But again, if you had anything other than, sort of really minor reductions, bless you, come and talk to me this week. Okay, either catch me at 8 o'clock tomorrow or Friday in the digital lounge, or regular office hours, and let's go through it. So let me go through some sample code. So nothing magic about this. I did this in one monolithic file. We'll talk in a little bit about splitting things up into files and having include files, and that was something that tripped some people up also, and we're going to go over that. But I just did this in one big file, so I had a single definition of my null, a single definition of a struct node, prototypes for my functions. So the 5 functions that you were required to write, plus I had some extra functions like process and usage, and then the 2 internal functions, get node and release node. So that's just prototyping. So the main program is very small. It declares an array of 100 struct nodes. No need to use malloc anywhere in here, by the way. Some people started to get fancy and did a lot of mallocs for dynamically creating the array. If you do that correctly, that's fine, but in some cases it gets you into more trouble than it helps. So for PA1, we have a single array of 100 struct nodes. That's our linked list. I have a string called buffer just for temporary storage. I initialize the list. That creates the empty list, just a sentinel pointing to null. Print a prompt, and then my main loop is just this, call fgets, and then I pass that to a function called process, which basically parses the input, does whatever it's supposed to do, and it returns a 0 if we're supposed to exit, a 1 if we're supposed to keep going. So if process gives back a 0, I just return from main. Otherwise, I put a prompt, go back up to the top. So nice short loop there. I've had a few people bring this up. If you have a function which is declared to be void, you can still use a return statement. Okay, just say return semicolon, don't return a value. Void doesn't mean you can't return from it. It means you don't return a value, a number, a pointer, anything. So you can't say return parentheses 5, but you can say return semicolon and kick out of the function anywhere. All right, so that's the main program. So all the parsing stuff I decided to throw into its own function because parsing is usually ugly. So buffer is the string of characters you're trying to interpret. So I switch on the first character to see what type of command. If the first character is an I, you said insert. I did something fancier here than you needed to do, which was make sure that you said I, number, and then nothing else. But you can just scanf with an I and a %d into num. If it returns a 1, it means it found a number. That's good. So I do all of this stuff. Otherwise, you said I, ha, ha, or you said I, nothing. And so I call my usage function, which gives you a help message, and I break out of the switch statement. So if you said I number, search the list to see if the number's in there. If it is, print a message saying you're already in the list and break. Otherwise, call the add function, and if it returns 1, it was successful. Otherwise, something went wrong. The only thing that can go wrong in add is you run out of memory, so print a message, no memory available. If the first character is a P, call the print function on the list and kick out. If it's an S, see if it's S followed by a number. If it is, search the list for that number and print out either found or not found, depending on what search returns. If it's not S followed by a number, print a usage, and then D is the same thing, and X exits the function. And if they type in anything that doesn't begin with one of those 5 letters, show them the usage. So that's the whole processing, right? And it's just the same thing over and over and over again. So dispense with that. Here's where we print out the usage message, so I don't have to put this in 5 or 6 different places in that code above. So this just tells them what they can do. And then here's the actual linked list code. So init, you did this in an ODP, set element 0 is next to be null. Set the valid flag. I put a magic number in the data, and then I zeroed out the valid flag in the other locations. Okay, straight ODP implementation. So add, we've gone through this on paper a number of times. Previous is the sentinel, current is the thing after the sentinel, which could be null. I make a node up front, so I call get node, make sure there's memory, store the data value, and now we loop looking for where to insert this new node. So I'm looping on the current node not being null. In other words, the current node is actually a data node. So if current's not null, compare its data value to the number we're inserting. If the number we're inserting is smaller, we want to insert right before current. So this just takes the previous node, points to the new node, and then has the new node point to the current node that we're inserting before. So sandwiches in between, and I just return right here. Otherwise, We're not ready to insert yet, so go on down the list one spot, move the previous to the current node, move the current to the next node, and iterate on that. So if you get out of this loop, it means you hit the end of the list and you didn't insert yet, so you have to insert after the last node. And the last node is previous, because current is null. So take previous, have it point to the new node, have your new node point to null, and you're done. And then print is just a straight traverse and print. So start off with the node after the sentinel. If it's not null, print out the data value, move to the next node, and just keep looping on that. And then search is the same thing, but instead of printing, we check to see if the current node's data value matches our number, and if it does, we return. So some people got nice and fancy in here and used the fact that if you're searching for the number 10 and you're moving through your list and you get to a number bigger than 10, you don't have to search anymore because you know your list is already sorted. So you can return a 0 right there. I was lazier than that, so I just searched the whole list until you run out of nodes. But that's a nice embellishment. And then delete. Same thing we've gone through again, so move through the list, and if you find the number you want to delete, take the previous node and point to wherever the current node is pointing. And that's pretty much it. The other routines are just the internal routines for allocating a node, freeing a node. So allocate a node. Search the array until you find an entry where valid is 0. Set the valid flag, return the index. If you don't find a node where valid is 0, you're out of memory, return null. And then release node. Release node, you're giving it the index of the node you want to release, so you just set that equal to valid. And there was some confusion around this in some cases. People were taking this as something that was supposed to look for a node whose data value is equal to num. That's what your delete function is doing. After your delete function has found that index 17 has the node we want to delete, it goes ahead, it sets the previous thing to point to the next thing. But then you need to take node 17 and say this is available now. So you call release node, you pass it that 17, right? That's the index number, and it just clears the valid flag. And some people just clear the valid flag inside delete, which works. But you can't do it in PA2. All right. So yeah, come and talk to me if you've got questions on your implementation, because I want to get it nailed down this week as much as possible.
So in PA2, our release function is going to free the memory we allocated prior
Mm-hmm.
using the free function?
And you just call the free function, yeah. And you pass it the address of the node you want to free. Mm-hmm.
Memory leaks are not permanent, right? Like after the program is done?
After the program's done, you're fine, yeah. Yeah, so they don't cause harm per se. The only time leaks are really an issue is if your program never exits, right? So if it's going to run for 300 days straight, it'll like chew up memory over time. All right, let's talk about include files and .h files and make files and all this other stuff. Because there's been some confusion. So I've got a new directory here, and I made a copy of my main.c in this new directory. And let's just do a little bit of modularization. So I'm just going to put some of this stuff into some different files. So 47. So I'm just doing some VI stuff here. So I'm doing a Control G. This thing starts at line 48, and I'm going to go down to the end of this. It's going to be probably everything. So I'm going to say :48, comma dot, write ll.c. So I'm putting that chunk of code into a separate file, and then 48, comma dot I'm deleting. And this is my main program now. So I've split my program into 4 pieces, right? A main program, a process function, a usage function, and then all my linked list code. I would probably split the linked list code into 7 separate files too, but we'll save time here. Okay, so this is not going to work, right? I could just try to compile everything that ends with a .c and put the output into an executable called main, and I'm going to get all kinds of issues here. Okay, the reason was when I had a single file, I had some stuff at the top, this definition of my null, including standard I/O, the definition of a struct node, and these function prototypes. Those were in the top of the file, and so when it gets around to compiling other pieces of this file, it knows what the prototypes are, what the struct node is, and so on. But this function ll.c, this file ll.c, I don't tell it what a struct node is. So as soon as it gets here and it says I want to take a struct node star as an argument, it doesn't know what that means. So what I should do is in the top of each of these files, I should put in all of this stuff. The prototypes, the struct nodes, type defs, defines, includes. I should put that in the top of all of my .c files. That's a pain. I don't want to type that in, and I don't want to have to change it in 4 or 5 different places if I change a prototype, for example. So what we do is we put all of this into one file, and we include that file everywhere that we need these lines of code. So I'm going to take all of this. So this is line 7. And I'm just going to call it ll.h. And I'm going to delete it from here. So now I have a file ll.h, defines, structures, function prototypes, type defs. Okay, no actual executable code in here. Right? If I compile this and run it, it does nothing. There's no main program, there's no functions. It's just information for the compiler. What is a struct node? What is my null equal to? What are the type of arguments that I'm going to pass to delete? What should search return? What type of variable? Okay, so that's what's in my .h. So now if I go into my C files, I can say include ll.h, and all of that stuff will get typed in right there, basically. So I'm doing, so I did a vi star.c to vi all of my files. So I just added this line in the beginning of the first one. I'm going to say :n, which says go to the next file. And I'm going to hit a period, which says repeat whatever my last command was, which was to insert this line. So I'm going to say :w to write, :n to go to my next file, hit a period, and keep doing that. And so I'm done with all my files. So now if I compile, I get a little further. I messed up a prototype. Oh, look at all those errors. Oh, I didn't delete it from main. Okay. Hey. All right. So, what have we done? my main program fits on one screen now. My input parser fits on a couple of screens, but that's all that's in this file is just this process function. But it can do things like call the add function, and the compiler is going to be perfectly happy with that because in this include file I have a function prototype for add. So you don't have to do this, right? You could simply type all of that right up here. Before you try to use add, tell it what the prototype is. Before you try to use delete, tell it what the prototype is. If you use myNull, put in a define statement. Okay? The include is just a way to save having to put in the same information multiple times in different files. And as I said, if you decide you need to change a prototype, you need to add a new function or something, I only have to add it one place, which is in the .h file. Yes?
Is there a way to like copy or move multiple files at once?
Sure. You're trying to move to a directory?
Yeah.
So you can say cp star directory or mv star directory.
And if you do like star.c, will it grab all the C files?
Yeah. So I make a directory called source and I say copy star.c source. And now if I go into source, it's got all my .c code. All right, so let's make a make file. Because I can do this gcc-o main star.c. But if I have other files in here that I don't want to compile, if I have a different version of main, I want to actually only compile these 4 C programs. And remember, make files are about efficiency. So if you're making a change to your usage.c, you don't need to recompile all of your linked list functions. You just need to recompile usage.c and then link everything together. So the make file lets us tell the system what needs to be compiled, what depends on what. So my main target is main. And it depends on these 4 object files. Main.o, ll.o, usage, and process. And if those are present, then there's how I build my executable.
So we don't need the .c.
You don't need the .c here because if I have the .o's, those are the compiled versions of my .c files. Once I've compiled them and I have .o's, I could delete those .c files and I can still link the O's together to get an executable. But if I ever want to change what the code does, I need the .c file. And then I need to make a change to it and then recompile that into a .o and then re-execute this GCC command. So this GCC is only the .o's. If I put the .c's, that will work, but it'll recompile every .c file every time I want to build a new main. And if I change usage.c, this will still go ahead and compile everything. So I use .o's there. And then you need to tell it how to create the .o's. Those are also targets. So main.o depends on main.c, and it also depends on the include file. If I change the include file, I need to rebuild main.o potentially. So I list the include file as a dependency, and my compile is gcc-c main.c. I don't list ll.h in the GCC line. GCC sees this statement that says include ll.h, it pulls in ll.h. You don't name stdio.h when you say GCC, right? So you don't name ll.h when you say GCC, you just say what file do I want to compile, main.c. But main.c includes ll.h, that's why I'm listing ll.h as something that main.o depends on. All right, so same thing for my other pieces, LL usage and process. And so that should be a good make file. So I say make, it compiles all my .c files, and it creates an output. Say make again, everything's up to date. If I change my usage.c and I say make, it recompiles usage.c and then it links the .o files together. Right? When I recompile usage.c, that gives me a new usage.o, and it gets linked with the other .o files into main. And say make, everything's up to date. If I touch main.c and I say make, it recompiles main.c and then links everything together. If I touch ll.c, that's all the functions that are used by everything. It still only has to recompile that one file. Get a new ll.o, and then everything gets linked together. Now if I touch ll.h, I change something in this include file. I've told it that every file depends on that include. So now if I say make, it recompiles everything. Since every file includes ll.h, if I make a change in there, theoretically I might have to recompile each of those files. So make does that. All right, does that make sense? Again, you don't need to do this. You didn't need to do this for PA1. You really don't need to do it for PA2. So ease yourself into it. If it's not clicking, right, don't let it hold you up on linked lists. You can do everything in one file. Your make file can just say gcc-o main, main.c, or pa2.c or whatever. But as you have time, and I'm predicting you'll have some time towards the end of PA2, right, go ahead and start messing with this. And it makes your life easier in the long run, in the short run now. All right, let's look at some GDB. So I've got some code here that's building a linked list. It's using our usual structure. So that's what our nodes look like. And I'm inside a print routine. I put a breakpoint here, and it was passed an argument that's called header. And header is supposed to be the sentinel node of this list. So if I print header, it's just a memory location. And last week we used the examine command X to look at things in memory, and we can piece together what this linked list looks like. But let's take advantage of the fact that this was compiled with GDB, with a G switch, and this means we can use the actual structure, the different fields, to examine this. So let's print header arrow data. That's a 42. And if I print header arrow next, that's some crazy address. So header is presumably a struct node. It's got a 42 and it's got a next field that's pointing somewhere. So 62CA. Well, I can do this. Header arrow next is this crazy address. if I say arrow data, arrow says go to this address, treat it as a struct node, and give me the data field. So if I print header arrow next arrow data, I get a 5. That's the data field of the node after the sentinel. So this is pointing to a struct node with a 5. And if I print header arrow next, that gives me another address, 62A0. So we're pointing somewhere, presumably a struct node. And if I print that node's data, there's a 10. And if I print that node's next and print that node's data, there's a 20. And there's a 30. And there's a 40. And we wouldn't normally write things like this. And there's a sig fault. So let's just print out this. Right, the data value of this node, whatever node all of this is pointing to. The data value was 40. Let's see what the next value was. Guess what? It's a 0. Zero is the same as null, basically. So with a few print statements, we can reconstruct on paper what our linked list looks like in the memory of the system. It's a sentinel with a 42, points to a 5, 10, 20, 30, and a 40, and 40 is the last node.
Oh, 0 set null. No.
Sorry?
Null equals 0.
Null is basically 0. But don't use 0 instead of null. Use null because it's actually an 8-byte 0.
But on PA1, null equals -1.
My null was -1, yeah. But in PA2 we're going to use null, and null is actually 0. Yeah.
If you use the define statement for my null and set it to -1, and you delete -1 and just type null there, will that have the same effect?
You mean PA2?
Yeah,
Yeah.
So for PA2,
Instead of my null, just use null.
yeah, but even though you're not putting a number for the defined value, since null is like one of those like end of
Predefined.
file, would it actually go through and replace everywhere you type my null with null instead of -1?
Try it again from the top. So if you do what?
So in my PA1 I have a define statement that
Mhm.
defines my null as -1.
Right.
If I delete -1 and just type null there.
Oh, define my null to be null?
Yeah.
Yeah, that would do the same thing.
Okay.
Yeah.
So the init function in PA2 just returns the memory address of the new node, right?
Of the sentinel, yeah.
Of the sentinel.
Mhm.
Then how do you use that node to begin, or like, what do you do with that memory address?
You pass it to, say, your add function. So
So you want to return it back to the main program?
So this is main. So you have a struct node star, call it list for now. We say list equals init. Okay, init allocates a chunk of memory, sets the next field to be null, returns the address of that piece of memory, so this sets list equal to that address. So list is pointing to basically the sentinel node. So if you want to insert 5, you could say add list, comma 5. And your add function gets 2 arguments. It gets a struct node star, which points to the sentinel and gets a number to add. Same setup as in PA1. Right? It was your first argument was basically pointing to the sentinel node. Same idea here. So previous equals whatever this argument is, current equals this argument arrow next, and start doing your loop and so on and so forth. And the point of the sentinel is that nothing we do is ever going to change the value of list, other than when we call init. Right? Nothing inside add, delete should ever change the value of this sentinel node. It's always going to be fixed at its location in memory. All right, so we can do these crazy kinds of things in GDB, and it's an alternative to doing these kinds of things, where we just examine memory locations directly. But both are fun to do. But particularly when you're debugging your code, right, you're trying to step through and you're about to say current arrow next equals new, right? You can print out the value of current arrow next, you can print out the value of new, you can make sure that current arrow next arrow data is the right value, and so on and so forth. So if you compile with -G, GDB understands all these pointer dereferencing operators. All right, well, that's a lot of stuff. So I will start off tomorrow, other than questions. I want to look at what we can do if we don't want a sentinel node. So the sentinel is optional, and I want you to use a sentinel in PA2, but we can live without a sentinel node also. I want to go over what that changes and why that motivates a sentinel. And then I want to talk about other kinds of linked lists. Circular linked lists and doubly linked lists are the two main ones. And then we'll go in and we'll switch gears. We'll leave all of this stuff for a little bit. We'll talk about hashes and hash functions and hashing. And then we'll come back to this next. All right, so I'll see you then.